Thank you for attending this presentation. Here I'm going to present the final project for this particular course. The way I've structured this presentation is into 4 parts. The first part I present overall CPU design. Second one, we dive into the assembler. Third part is about the emulator, and finally wrap it up with the hardware implementation. So the overall CPU is the key features related to the CPU are listed here. The important thing is that the CPU is word aligned, and each word is equivalent to 2 bytes. Then I present all the block diagrams for the different instruction sets that are being supported by the CPU. A key word about the registers that are being used: there are a total of 16 registers. Initially I started out with them being general purpose registers, but then as I proceeded on, some of these registers were assigned key particular values. So register 0 is always equal to 0, register 1 is used for storing the stack pointer, register 2 is used for storing the return address. Aside from that, I've listed out the CPU instructions that are being supported. This is a exhaustive list of all the instructions, and here I have listed it out in terms of the ops and function code for the different instructions. Following this, the presentation also contains all the different types of instructions and also the assembly code for each of these instructions that can be used. Aside from that, a key highlight is that for something like a load word instruction, I'm supporting it using either when the memory is referenced by a variable, or if the memory is referenced by the actual address. So there are two different types of implementation that I have for load word. Aside from that, I'm supporting one pseudo instruction, which is that of the load address. From here on, I'll go into the assembler. The assembler is structured such that I have a main.cpp. I also have two header files, instruction.h and constant.h. Aside from that, I also have a cpp file which is instruction.cpp. The function of instruction.cpp is that it contains all the functions which are then called into main.cpp. Aside from that, a few salient features of the assembler is that I can support two directives, ASCII Z and data. Aside from that, I'm able to support symbolic constants to refer to data, and I'm also able to use one pseudo instruction, which is load address. Let me go into the terminal and give a live demo of this assembler. I would be running an assembly file which I have prepared, which looks something like this. And then let me quickly load it up. So what I see over here being run is that I'm logging each and every line in the assembly file, and I'm able to see what the instruction is, and I'm able to see all the associated properties with that particular line in terms of what is the registers that are being invoked, what are the immediates, and so on and so forth. Aside from that, when I'm able to go back and look into the MIPS file that is being generated, so this is the MIPS file which is generated, I'm also able to log the comments which are associated with a particular line in the assembly file. So like, for example, I have this comment over here that gets logged into my MIPS file. So with that, these were some of the main features of the assembler that I wanted to highlight. So next up is the emulator. I have listed out the key takeaway for the emulator on this particular slide, but let's just go ahead and look at the code. All right, so here I've shown the overall structure of the emulator, and I have the main file. One of the features of the main file is that it is capable of doing error handling while the file name is being input. So without spending much time looking at the code, I just want to give a live demonstration of this. So I've come into the terminal window, and I already have a MIPS file prepared. This MIPS file does nothing but just, the assembly code does nothing but just ask for input from the character, from the user, and then it stores those characters inside memory. So I'm going to execute that. The execution could either be done in the debug mode or just run through it. So I'll just select no for the time being, and then I just run it. It asks, and the program now asks me to enter character. So let's say I enter B, it asks me to enter another character because I'm simulating the input stream. So I input character O, and because I'm not able to enter null character through my Windows keyboard, so I'm just simulating that functionality by the character Q. So as soon as I enter character Q, the string gets ended, and I'm able to see these two characters being stored in the memory. Now let me run the same program in the debug mode. So when I run in the debug mode, I'm able to execute through each line in the MIP file. And here I see what is the first word which is stored in the MIP file. I'm able to see what is the decoded assembly code because I also have a disassembler. And I'm also able to see what is the register value before and after execution of the code along with the program counter being displayed. And then I can just step through it and keep on taking a track of how the program is running. So finally we come to the last part of the presentation and this is related to the FSM sequencer and the hardware. The topics that I would go over for this part are all listed here, but instead of looking at this, let me just pull up the relevant documents. So first up, the clocking scheme that was used for the hardware implementation is shown here. And this is similar to what we have discussed in the class, wherein on the falling edge of the clock, all the FSM state advancement takes place. Then on the stable edge of the clock, all the gate propagation and setting of combination logic happens. And on the rising edge of the clock, all the registers are being set. From there on, I will show the sequencing of the different states and what it depends on. So here I have listed out all the different states that are there in my FSM. There are quite a lot of them. I think it's approximately 40. And here we have listed out all the different control lines that are getting asserted as we move from one state to the other. Before starting or before implementing in the hardware, there were some states which I thought would be required. But in the end, I realized that either they are already provided to us as a memory system, for example, memory data ready inverse, or perhaps I don't need them. For example, I didn't need clearing the program counter because that was already happening at the reset of the memory. So that was not required. So I have made a note of things which I didn't require, but initially I thought I would require them. From there on, I go ahead and show the code of the hardware that was implemented. This is the overall top level entity that I have. There are also a bunch of different component files that are being used, which are listed all over here on the side of the window. But in the top level entity, first we define all the inputs and outputs, and then from there on I define do the chip pin assignments, and then also call in all the components which are being used from the different VHD files. Then in the middle portion of the program, we do the port mapping, and then at the second last end of phase of the program, I go ahead and do all the combinational logic setting of the different signals and so on and so forth. And finally, we see over here the FSM sequencing, which goes from one state to the other. So in this first demo, we are showing that we have to print out the number written in a register onto the secure terminal, and the data which is stored in register 5, which is 1919, the whole idea is to get it printed onto the terminal. And this particular assembly file has a lot of different instructions such as branches and JL and so on and so forth, and this is the MIP file that is being used. From there on, we just load the MIP file onto the system, set up the terminal window as well as the camera in which the hardware is visible. And there what I did was that I first reset the hardware, and then on the hex displays I see the instructions being displayed as well as the program counter value progressing. And then on the terminal window I can see the numbers starting to get generated, all secure CRT, and I see -19 being generated there. In this particular program, the idea is to take a number which is being input on the terminal and then store it in a register. In this case I would be using register 5. Just like the previous demo, I load the particular assembly file into my hardware, set up the hardware in the run mode, and then on the terminal window I'm able to input this number, which is -12, and then the hardware just keeps on running, going from one state to the other. And then as soon as the program finishes running, what I do is that I set my hardware so that I'm able to see what is there on register 5, and here I've set it and I'm able to see the value on register 5 is at F4, and then I check the number and I see it is indeed -12. Before getting into the demo, I also would like to highlight that I did build a test bench for the final project, and this test bench was a lifesaver in terms of debugging the program. I've shown it over here, and the different things that I was able to display and be able to debug were just amazing. All right, just want to give a demonstration of the final program where we show number multiplication using the hardware. So I have the system set up over here. We can see the hardware on the side, and also I have the program loaded onto the Altera D2115. I have the secure CRT window running. Let me just resize it so that it fits into the window. And yeah, from here we are good to go. I'll just go ahead and start the um, start the clock so that we can start with the program. So I reset it and just start the clock, and as soon as I start the clock, I can see the prompt is shown to give me for me to enter some number. So just enter a few number in at random. So it takes a bit of time, but we'll eventually get through it. Case 4. So pretty much we are just taking two numbers, multiplying it, and then I'm just displaying the product of those two numbers. So I'll just do it with a couple of more examples just to add more variety to the inputs. So as to say, 4 um, 43 perhaps. Yeah, the software multiplication does take some time. I did try uh, playing around with the clock. For some of the clock inputs, I did observe the product not being computed in a manner that seems accurate. Um, not entirely sure whether it's happening because of the clock or whether there's some errors in, or whether there are a lot of gates in my program which is causing that. So not quite sure of that. But yeah, the hardware multiplication does take some time over here. Oh, sorry, I meant to say the software multiplication. Yeah, hoping it would, the number would show up. Usually it is taking some time for the computations to occur. One of the next steps that I would like to take, which is kind of going above beyond right now, is to play around with the clock and seeing exactly what could be done to speed up this process, aside from hardware multiplication, implementing an hardware multiplier itself. So that's some of the next things that I would like to do beyond this course as well. All right, I just do one more number, wherein I feed something like 5, and then let's do something like -20. See what that gives. Just want to quickly show the results of some more computation for multiplication. So aside from the demo that I just right now gave, I also ran multiplication for a bunch of different number primarily to test the edge cases, and I've listed them out over here. So as we can see that the program is able to handle multiplication right up to the range as what we are requested to do, can handle both positives and negatives and so on and so forth. Thank you.